Hey class, and welcome back. This here is going to be a short lecture about the last chunk of chapter 4, section 7 actually, about the gravitational force. But to really get the most out of our understanding of the section, I want you to watch chapter 5 and look into uniform circular motion first, because gravitation offers some really interesting examples of the gravitational force and some of its applications to satellite motion and that kind of thing. So make sure you watch that first. Now, if you have, we're going to continue and talk about the force due to gravity, the gravitational force, and some of its cool applications. So you ready? Here we go. So as you're about to see, this section is really centered around Newton's conception of the universal law of gravitation. As you'll learn possibly as we go on in your education, that Einstein really revolutionized the way we understand gravity when he came up with his special and general theories of relativity. But for now, we're going to just talk about how Newton described it with his law of universal gravitation, which is a very good approximation in most applications, although current theory believes Einstein's sort of conception of gravity to be a more accurate way of describing it. But physics is still a field that's alive and well, and there's still some mystery and question around how best to really model, describe, and explain gravitation. So what Newton observed and determined is that he said that really there seems to be this attractive force between any two particles anywhere in space. Everywhere in the universe, any two pieces of matter are going to naturally, gravitationally attract one another. All right, so that means if I walk by my wife, I will feel a natural attractive force towards my wife, which I feel anyway because she's amazing and beautiful. But also, physically, there's actually a gravitational force of attraction between the two of us as a result of being two masses near one another in the universe. And so the same could be true, you know, saying, okay, here's my water bottle. Since I'm a mass next to my water bottle, there's a natural gravitational attractive force between me and my water bottle. Not nearly as exciting as thinking about the attractive force between my wife and I, but still a good example. So really, any two objects anywhere in space experience this natural attractive force due to gravity. So yeah, one easy example of this is to think about the Earth and the Moon. So the Moon, believe it or not, is held in orbit around the Earth by the gravitational attractive force between the Earth and the Moon. So you can either think about it in terms of the big Earth and the big Moon, or you can even think of the Earth and the Moon as 2 point masses some distance r apart from one another, and they're going to experience this natural attractive force just like me and my wife, me and my water bottle, any two things anywhere in space. All right, so how did Newton actually quantify this gravitational attractive force? Well, he came up with an equation that says if you have any two masses, m1 and m2, that are separated by some distance r, that gravitational attractive force, F here, is the force of gravity, is going to be equal to this equation, g, which is the gravitational constant, multiplied by mass 1, multiplied by mass 2, and then divided by the distance between them squared. All right, so g is the gravitational constant, which we actually introduced briefly earlier in the semester when we're looking at dimensional analysis. But g is equal to 6.673 times 10 to the negative 11th power, and our units are newtons times meters squared divided by kilograms squared. So if you notice, 10 to the negative 11th power, this is a real small number. That's why when I have my water bottle sitting here next to me, and I'm sitting here, it's not magically, boom, being drawn and sticking to me, because my wife wanted a replay, boom, like that's what would happen if g was not such a tiny number. But because it's so small, the mass of the water bottle and my mass were not hugely massive. Okay, at least I try to eat healthy. No, okay, just kidding. Anyway, because our masses are relatively small, even if our distance is very small, we're very near one another, that attractive force is still very, very weak since we're multiplying by 6.673 times 10 to the negative 11. Okay, so again, this is the force of gravity. The closer two objects are, since that's on bottom, the larger the force, and then the more massive either object is, the larger that attractive force as well. So I always like to tell a joke, you know, I would like to warn anybody that knows their physics, if you're interested in, you know, a guy or a girl, you think they're cute or whatever, and you want to, you know, go and talk to them about maybe going on a date or something, you have to be careful. If they know their physics and you walk up to them and be like, hey, you're pretty attractive, I want to go on a date with you, they might think you're calling them fat. So be careful, all right? More mass means more attractive force, all right? So while my wife is beautiful, I don't usually call her attractive in case she misinterprets it, knowing her physics. So, all right, that's a bad joke, I'm sorry, but it's the best I can do. So with that in mind, let's actually calculate. What is the attractive force between two students sitting 0.75 meters apart? All right, so here's a guy and a girl. The guy has a mass of 75 kilograms, the girl 55 kilograms, and they're 3/4 of a meter apart, 0.75 meters apart. Go ahead, calculate the gravitational attractive force between these two students. Ready, go. Dun, da, da, da. Hopefully you did the calculation using Newton's law of gravitation. Thinking about this force, it's equal and opposite. All right, Newton's third law tells us that it's going to be equal and opposite, so they both will feel the attractive force in opposite directions. Both of them will feel that attractive force towards one another. Keep in mind this r distance. This is a common mistake people make. This r distance is the distance between the center of mass of your two objects. So it's the 0.75 meters. It's the distance between the two students. A lot of people want to divide that in half because they think radius is half of that distance. No, r is the distance between the two objects. All right, so if you plug and chug, what you would find is the attractive force between these two students is a whopping 4.9 times 10 to the negative 7th power newtons. So it's actually very small attractive force because, again, that gravitational constant is such a tiny number. But boom, my friends, that is once again box worthy. Yeah, so here's another little trickier example for you all. Because of this idea of gravitational attractive force being dependent upon the distance between your two masses, all right, as you increase in elevation, as you move farther away from the center of the Earth, you would actually have a smaller apparent weight. All right, we say weight is just mass times gravity, 9.8 meters per second squared, but that's actually an approximation, assuming you're at sea level. If you're not at sea level, if you're higher above sea level, your weight would actually decrease. That gravitational attractive force would actually decrease because you're further away from the center of the Earth. So here's an example I want you to try out with this. Okay, I'm a big fan of Ernest Shackleton and his exploration of the Antarctic. And so in honor of him, here's an example problem. Imagine that you had a person with their gear and everything on. They have a total mass of 108 kilograms. All right. And so I want you to tell me, what is the difference in weight for this person with their gear on? If their mass is 108 kilograms, what's the difference in weight between when they're standing at sea level, when they first get onto the Antarctic continent, versus when they're atop the mountain peak of Vinson Massif, which is a high mountain peak in Antarctica with an elevation of 5,150 meters above sea level. All right, I want you to figure that out. To make your math a little bit easier, I went ahead and multiplied g multiplied by the mass of the Earth for you here. Okay, if you don't like that, that's fine. You can still use 6.673 times 10 to the negative 11th for g, and then look up the mass of the Earth in a data table as well. But figure this one out. Ready, go. What is the difference in weight, strictly from this person being at two different locations? So hopefully you paused it and tried it out. Again, we're using Newton's law of gravitational attraction here. If we calculate it at sea level, you could just use their mass and multiply it by 9.8. That's a little bit of an approximation, so I went ahead and used the actual values. So here's g times the mass of the Earth, because that's our first mass, and here's the second mass. Now notice, for the r value, this is a tricky part as well. What I used here is the radius of the Earth. Why did I do that? Because it's the distance between the center of the two objects. So if you're standing at sea level at the outer edge of the Earth, then that distance between your center of mass and the center of mass of the Earth would just be the radius of the Earth. So that's why I use the 6.38 times 10 to the 6th meters. That's the radius of the Earth. So if I plug and chug, the gravitational force at sea level comes out to be 1,058.66 newtons. And on the mountain peak, we do the same thing, but now the radius, the distance between the center of mass of our person and the center of mass of the Earth, becomes the radius of the Earth plus that additional 5,150 meters. Once again, plug and chug, doing the math, and you find that the weight, as expected, has decreased since our radius has increased, and that's on the bottom of our equation. It's decreased down to 1056.95 newtons. So you think you might be done, and you almost are, but we're asked for the difference in weight, right? So for the difference in weight, we need to take the weight at sea level, subtract the weight on top of the mountain peak, and what we would find is that our delta, our difference in weight, is 1.71 newtons. Boy howdy. Cool, good. So again, going back to this idea of weight, we've defined weight as being equal to mass times gravity so far, right? Well, that's really just a special case of using Newton's law of gravitational attraction for some given mass, the mass of the Earth, and assuming you're at sea level, so plugging in for radius, the radius of the Earth. So what you can see if you look at this equation, look, if this m here is just the mass of you, me, or whatever we want to find the weight of, then g, the acceleration due to gravity that we always use as 9.8 meters per second squared, must just be equal to the gravitational constant capital G multiplied by the mass of the Earth divided by the radius of the Earth squared. Don't believe me? Well, fine, I'll prove it to you. Plug that in. Look, G, the gravitational acceleration, is just equal to the gravitational constant, mass of the Earth, over the radius of the Earth squared. Plug and chug with all those numbers. Here's the mass of the Earth, as we mentioned earlier. And you find that G is equal to approximately 9.81 meters per second squared. Okay, so the next thing I want to talk about here in dealing with chapter 13 in gravitation is the concept of satellites and orbits. So if you think about a satellite, there are so many, there's thousands of satellites buzzing around the Earth right now. It's actually kind of crazy how many satellites there are. Used for everything from GPS to cell phones to television, all kinds of different things. Satellites are being used for weather tracking and all sorts of things. So what is it that keeps satellites in orbit? I'm guessing you figured it out by now. If not, you can look at this picture and it'll tell you, but it's the gravitational attractive force. Gravity between the Earth and the satellite keeps it in orbit. All right, so the question then is, how fast must a satellite be moving in order to stay in orbit? Because believe it or not, there's actually just one specific velocity that a satellite can have if it wants to maintain a circular orbit around the Earth at a fixed distance. All right, if it goes too fast, its orbit will get oblong. It'll become an oval-shaped or an elliptical orbit. If it goes too slow, its orbit will shrink down some. So if it wants to keep its specific orbit, there's only one fixed velocity to maintain a circular orbit. So the question is, how can you figure out what that is? Maybe pause it, think about it. What forces are acting on the satellite? What role is gravitational force playing, and how does that relate to how fast it's moving? Newton's law of gravitation doesn't say anything about speed. What's the deal? Pause it, try to figure it out. All right, if you thought about it, there's a reason why I'm doing chapter 13 right after chapter 5, and that's because the force of gravity from the Earth and the gravitational attractive force between the Earth and the satellite, that force is keeping it in uniform circular motion. So that means that that gravitational attractive force is supplying the centripetal force required for this object to stay in a fixed orbit. So again, if we know net force equals mass times acceleration, if the only force is the gravitational attractive force, that must be equal to the mass multiplied by the centripetal acceleration that the satellite has since it's in uniform circular motion. So gravitational attractive force must be equal to mv squared over r. And this will enable you then to solve for the speed at which the satellite must be moving to maintain its orbit. Keeping in mind, this speed is in the perpendicular direction, perpendicular to the radius, right? So if you notice, look, the mass of the satellite cancels out. Whoa, boy howdy, the speed that we're going to find is going to be the speed for any satellite of any different mass. That's cool. One of the radius values cancels out. You take the square root, and what you find is that the velocity that it must be moving at is equal to the square root of g, the gravitational constant, multiplied by the mass of the Earth, and then divided by r, where, keep in mind, this r is the radial distance from the center of the Earth to the location of the satellite. All right, so that's the radius of the Earth plus whatever additional altitude the satellite has. Most satellites are hundreds or thousands of meters above the surface of the Earth. So the R value would be the radius of the Earth plus that additional altitude. But it's that one fixed velocity that a satellite must be at to maintain an orbit at that distance above the Earth. All right, so again, it's one set speed that it must have to maintain a fixed circular orbit. All right, so there are elliptical orbits. Its speed can vary, and you can have slightly different speeds for elliptical orbits, but for now, we're going to just focus on looking at circular orbits. So what would happen at different velocities? Well, as we just mentioned, at different velocities, you can get elliptical orbits, and if you keep going faster and faster, in fact, your speed can become so high that you would achieve a speed at which you would have what's known as an unbound orbit. So the gravitational pull would cause you to bend or change direction, but you'd be going too fast to get caught in orbit around the Earth, and as a result, you'd be flung off into space in some different direction. And you actually see unbound orbits happen a lot, especially in like space movies and other science fiction type movies. They do gravitational flinging around planets and so on, as you see in, I think The Martian had it as well as other movies. Okay, so the gravitational force still affects it, but it will have different types of orbits based on speeds away from that one set value that we just talked about. So that's fun and good. Let's do an example problem using that idea. So here's a picture of the Hubble Space Telescope. Really quite a powerful tool for finding images of different things throughout space. It's been able to get some amazing imagery and also helped us to learn a lot about the universe around us. So the Hubble Space Telescope, it orbits at approximately 598 kilometers above the Earth's surface. Based on that information, and I give you the radius of the Earth and the mass of the Earth here as well, based on that information alone, I want you to tell me what is the speed of the Hubble Space Telescope. Pause it and give it a go. All right, so as you probably figured out, we are going to use the speed equation, the velocity equation we just derived on the previous slide. So we have g, the gravitational constant, the mass of the Earth, and down here is r, where r again is going to represent the distance from the satellite to the center of the Earth. So in that case, it's going to be this 598 kilometers plus the radius of the Earth. So if we do that, plug and chug, keeping in mind we need to convert kilometers into meters, so times 10 to the third power you see here. Plug and chug, do the math, and you should find that the Hubble Space Telescope is moving at approximately 7.56 times 10 to the third power meters per second. So it's moving at 7,500 meters per second, or almost 17,000 miles an hour. It's cruising, moving real fast. Cool. So that's fun and good. There's a lot of times, though, we want to pay attention not just to how fast a satellite is moving, but we're really interested in the orbital period. As you'll see in the next slide, one major application of looking at satellites in terms of their orbital periods is GPS, global positioning. Works based on the fact that there's satellites centered over a certain portion of the Earth's surface, and it stays above that portion of the Earth's surface all the time. So what that means then, since the Earth is constantly rotating on its axis, you need to get a satellite at a distance above the Earth such that its orbital period stays at 24 hours, so that it takes the same amount of time for that satellite to go around in one orbit around the Earth as it does for the Earth to rotate once. And so what we're going to do now is we're going to derive an equation for the orbital period of a satellite to tell us how high above the surface we might need if we want a 24-hour period or something like that. So I want you to pause it. Based on what you know so far, see if you can figure out an equation for the orbital period. Ready, go. Well, if you start with the equation that we just derived, velocity is the square root of g times the mass of the Earth over r. And we know that velocity for something in uniform circular motion is equal to 2 pi times the radius over the period. You can just do a little bit of algebra, solve for t. Multiply by t, divide by everything on the other side. And what you should be able to figure out is that the period is equal to 2 pi times the radius to the 3/2 power. Where does this come from? People get a little confused. Well, what you end up having is radius to the 1 power, and then we're multiplying by the square root of r, which is r to the 1/2 power. R times r to the 1/2 power. You add the powers when you multiply, so r to the 1 plus 1/2, 1 plus 1/2 is 3/2. That's where that comes from, okay? So that's the equation you get for orbital period. It'll be useful on the workshop and some other places as well. But for GPS, as I mentioned, there's satellites that are over a fixed location on the Earth all of the time. Actually, there's multiple in any given spot, and it's triangulating amongst these different satellites that gives you your GPS location. And so they all must have an orbital period of 24 hours in order to maintain constant knowledge of your location as you're trying to drive from here to, I don't know, the grocery store or wherever you're headed. To Disneyland, yeah, that's a better example. My wife said she and I both love Disneyland. So let's say we're driving to Disneyland. We'll use a lot of different GPS satellites on our way down there. And not only will the physics be fun, so will the rides, which also have physics. So there you go. Fun all around. And ice cream. My wife loves those Mickey ice creams. I do too. Who am I kidding? Anyway, so that wraps it up for chapter 13. Let me know if you have any questions, and maybe we'll take a field trip to Disneyland. Okay, we won't, but I wish we could. All right, have a box-worthy day.